Hey, how you going with your family journey into algebra land? Hope you're enjoying it and building up some ideas and skills there. So look around the screen. We've got some of the stuff we've been looking at. Here, these tables from Tink. We're going to move away from Tink shortly now, but have a look here. What's happening here? I think we're using the Casio to display members of the family. I don't know. We're going to look at this idea. What numbers have I put there? And what's this? I mentioned this earlier presentation. This is a little plot or a graph of the family members and something. Don't know. Well, let's have a look because this looks interesting to list our members in different ways and to look at the families with a different approach. So it's another look at mass families is what it's called. So come on down and let's have a look at this family that I mentioned up there. And oh, look what's happening down here, mate. Oh, lots of little screen clips from the Casio calculator. So we'll have a look at that in a minute. So here we are. We've got our classic little structure of what's going on with our family members. This is a family multiply by 2, subtract 1. Okay, so we could put that down. What is the algebraic expression? 2x take 1. Okay, and here we have the x value or the generation number, and here we have the actual first name or family member. Okay, remember that? We're generating families here with varying values of our unknown generation number x. I hope you're getting the hang of that. You might have to go back over some of the earlier presentations if you're not sure. So I want you to get out your Casio 9860 there, 9860 Plus or whatever you've got there, Graphics Display Calculator, and I want you to bring up the menu. So on the keypad, can you hit menu? And you get this window, and I want you to scroll around, and you can use the big button, which is like this, to scroll around and come and highlight stat mode. Okay, and if you push execute, you get this window. And what I want you to do is into list 1, I want you to enter all the generation numbers here. These here go in there. You can see I've already done it. And then I want you to put the family members in here. We're going to try and link up the generation number with a family member, because they are linked, aren't they? Very, very closely linked, because that's the number that you operate on, Tink operated on to get the family member. Okay, so now if there are already entries in here that you don't want, down the bottom, I haven't shown this, you can hit del for deleting those columns and just go down and delete all the entries that are in there. All right, well, you might have to pause the presentation. It'll take you a little while to set that up. And when you come back, here we go. I want you to hit set now. So you hit that by the key underneath, F6. And up comes this window here, okay, this little window here. And I want you to change the graph type to scatter. So you might have to go on to the next window. Depends on how your calculator is there, what window it's on. You've got to find scatter graph, okay, that type. And up will come X list. X list, I understand that. So that's where you're going to put the X. Hey, what's this? They've got another letter here, another pronumeral. I wonder what that's about. We're going to see that in this presentation big time. So into the X list, list 1, you want to make sure this entry is there because that's where you put the generation number. Oh, it looks like they're going to call the family member Y here. Now that's an interesting innovation. And we might adopt that ourselves in a minute because technology uses X's and Y's to represent unknown or numbers and standing for pronumerals. Okay, so into list 2, you've got to make sure you're telling the calculator here where the X number is and where the family number is. And each of them is occurring only once, so that's okay. And it's going to mark the type of little plot there with a square, so that's okay. All right, so if you then push exit there on your calculator, find that exit button. I should have put all the whole window or the whole calculator face there, but hit exit, and then I want you come back to this one, I want you to hit select over here. It says which graph you're going to draw, because the Casio can actually be set up with 3 graphs in stat mode all at the same time. So stat graph 1 is the one we want, so you need to scroll to there with the big button and put draw on, and if you hit draw, then you get the graph. You might have to pause and play around with that. Depends on how much experience you've had with the Casio. Alright, come down now, and that's what you're going to get. Now, what have we got there? Well, let's try and work it out. The calculator said we wanted the X list 1. So, okay, it looks like this is the value, these are the values here that we had for the X list. So, this must have been the family members up here. Okay, see the scale is different? So this is a family member, and they called that Y in calculator land. Or we could have called it, what was the expression there? 2x take 1, wasn't it? We could have done that. Okay, could have labelled that axis. We call these axes actually, and this, we call this the X, and we're going to start thinking about using Y to represent that family member. At the moment, you can think of it as 2x take 1, but the calculator said they wanted to call it Y in there. Okay, that's not a bad idea, is it? So we can see, as you change the generation number here, so the family member changes. Now, this is a nice little picture of what's going on. The fact that as you change the generation number, each of these goes up a certain distance, and it's a straight line, isn't it? That's special. I wonder how that happened. Okay, change the generation number by 1, and it popped up by the same amount, keeping the line straight. Wow, that's some interesting maths. We'll come to that later on. Let's go on and see if we can do some of this. Okay, so coming down here, representing families of numbers, let's summarise what we've done. The first way of representing families was in Tinkland, and that was just to put down what we're calling here a structure table. Okay, it's a fairly clumsy way of representing it. We've seen some neater ways, and we're going to do that in a minute. This is listing down, if you like, the operations that's going on, or the structure of our family, how you get the family members. Okay, that's one way, and we've done that. Representation 2, this is important, 2x take 3. Let's just go back up and have a look at how we did that. So remember we said we're multiplying by 2, here it is here, in each case, so it's all the same family, they're the same, remember what's the same and what's different. So we're multiplying by 2, this goes right back to the beginning, and then we are doing this thing over and over, that's the same as well, subtracting 3. And we said, well, if this is a number Tink thought of, that's a generation number, we could say it was 2 times x take 3, and in our algebraic expressions we say, well, we don't really need that time sign. We can make it neater by just putting 2x on our special mathematical language, our special algebra jargon, if you like, of 2x take 3. Remember that stuff. Doing a little bit of revision for you there, mate. Okay, now, can you see how this would capture all the members of the family? Okay, because they all follow this pattern. How many members would there be? How many different values of that generation number could you put in there? Oh, heaps. Would be an infinite number of members, wouldn't there? You just keep going, mate. We're going to have a look at that as well shortly. Come down now and let's look at the representation 3. Now that's what we've just been doing, where we put the generation number and then next to it we put a listing of the family member that mates up with that particular generation number. So who is generation 6? It's 9. Easy to pick it out from this particular table. So you've got the generation number and then the family member over here. Nice and closely associated to each other so you can see what's going on. Who is generation 8? Here's generation 8. That is the family member 13. Okay, and this building, once you keep thinking about this journey into algebra land using families is important. And there's our last one, a graphical display. We can actually see the journey in generation number as we go along here. What's happening to our 2x take 3? Look at that. What's happening? And we can see every time we change generation one number by 1, we go up by there 2. Change this one by 1, we go up by 2. Hey, that's the reason for the points line in a straight line, isn't it? What makes a line straight? Hey, that's a question for later. What makes a line straight? Okay, rather than curvy, a little few bumps and stuff. Can you see? Okay, I'll just do it again. You're going up by 1 in X land, and your family member goes up by 2 every time. That might have something to do with keeping the line straight and not making a curve. Think about that one. That's going to come up. That's a bit of excitement for later on. Okay, come on down. I want you to do some stuff. And here we are. And I guess we already knew that. The calculator told us first, mate, that it wanted to call the other varying quantity there, the family member, y. The family member. And so here, this was another connection between the family member and the generation number. Okay. What we've done now is made something new. Look at this. We've introduced a second pronumeral to take the place of the family member, the first name. And we're calling this an algebraic equation. What? What's that? Equation. Equation. Oh, I think that comes from the word to equate. Okay, it does, to equate. We'll put equals because it includes an equal sign. Shouldn't have a D there. It includes an equal sign. So 2x take 3 is an algebraic expression. No equal sign, mate. But y equals 2x take 3 is an equation, an algebraic equation. And why do they both belong in algebra land? What do you think? What are you thinking about algebra now? Lots of families of stuff. But we're using pronumerals, aren't we? To stand for various quantities that could be changing. Okay, so that makes it algebra land when you see these x's and y's. And we could talk about expressions or equations. Okay, can you see it's nicely building in a very commonsensical way? Our families are growing. Let's go down and have a look now at another way of approaching the Casio. Okay, so here we are. Oops, that's no good. We're almost there, mate. Okay, so here we are using the Casio. Just come down a little bit. There we have it. All right, we're going to go into a different mode on the Casio now, one that will produce a table and a graph. Stat mode, we didn't put in a formula, we just put in the raw values for generation number and family member. Now, we could journey in here because we have an actual equation, and there's another area on the calculator that allows you to put this in. If you know the algebraic equation, you can put it into, come over here, choose this on your calculator, table mode in the middle there. And it's going to create a table and a graph. Two forms of representation of our family that are interesting, and we want to do that. So if you put execute, once that's highlighted there, scroll across, highlight it with execute right down the bottom of the keypad there, EXE. So that's how we operate the Casio. If you don't know that by now, maybe I should have put the whole screen on, the whole Casio on again. Anyway, so you come to table mode. That's that table. Hey, there it is. The Casio likes Y big time, eh? So there's all different families you could put in there. I want you to use the keypad. So go down to number 2 down on the keypad, 2, and then you've got to put in X in here. That's the X. So come to this one here, X, theta and T, because as you go on in maths, you'll find we don't always call the varying quantity, the generation number, X. We don't do that always. We can use other things. So here, going to hit X, and we'll get 2, and then hit that button X, and then take 3. Now take is right down the bottom of the screen, way down on the second to bottom row on the right. So find that take. Now there are two of them. There's that one and there's one with a bracket. We're going to leave that one for the minute. Don't put that one in. That's a negative sign. So we're going to use take and then put 3. I want you to enter that. And if you push execute, and we'll just rub that out now. If you push execute, can you see that the equal sign in there becomes highlighted? So it says this is the function, this is a little expression, this is the equation that the calculator is going to work with. But now you've got to tell the calculator what you want, so you've got to set it up here. So you have to select set as before. You will hit F5, the buttons under it select those particular icons, and you end up with this window. Okay, so now look at what I've done. I've started the table with a table setting X with a generation number of 1 and going right up to 20. Hey, that's a big table, mate. You could set it at any value. You could set it from -3 to 3, start and end, and it's going up in steps of 1. That's what we usually do. So this -3 can be a bit problematic, because I'll just unravel this down here. I said before, right down the bottom, there's a row where you've got the subtraction button, and over here, there's a negative button. So if you want to put -3, that's the one. The negative sign with a bracket around it makes it -3. So you could go -3 to 3. You could put all sorts of numbers in there. How many? Infinite number. Okay, well, let's go to the next window, right over here down the bottom here. Come over here with me. And we've set it up and we push exit. So we've got to have exit first, and then we come to this window and it's ready to go. So you will now hit in here, follow this table. To get table is F6, down underneath it there, and you create the table. So we've got, hey, give this a few ticks, mate. We've got a nice table to look at our X and family member, our generation, and what are you going to call it? Y maybe for the family member. Calculator certainly wants to do that. And we can see there's some patterns here when generation number is 1, family member is -1, and so on. Okay, well, how about a little bit of a graph? Okay, well, let's have a look at GPLT. It means Gplot, plot the points. So to choose that, we need to come into this button here, F6, and there we have it. There are our points. See them along there? I'll just go them in a bit more. Okay, so there are our points along there. Okay, so how about that? That's not bad, is it? Now I'm going to do a little bit of a trick on you now, and I want to see if you can answer a question. Can you come right back over, here we are, to this window here again. We're over on this window, and then you can see there Gcon. Gcon. I wonder what that might mean. Well, if you hit F5, means graph connect. Ah, here it is. What's the difference between those two graphs? What has been done? Okay, well, Gcon might be a bit of a hint to you. Graph connected. Hey, the points have been connected. Okay, I want you to think now. You might want to pause the presentation and maybe discuss it with your classmates and your teacher. But is there a difference in mathematical meaning between this one, separate points, and join points? Okay, pause the presentation and have a little discussion. All right, we're back again. Hey, if you connect the points, what are you suggesting? That values, there's 1, there's another point. This could be 2 in X land, that could be 3. If you join them, can you see that you are suggesting that the pattern or family member could have a generation number of anything between these two, like 2.2, 2.3, 2.4. Can you see that? that connecting up the points is a very, very important mathematical idea. It is saying that we think the pattern of 2x take 3, y equals 2x take 3, continues for all values in between the ones that we have put in there, the integer values. Now, would that be true for 2x take 3? We said before, x could be any number. It could be 2.1, 2.2, couldn't it? Would we be able to work out that family member if x was not an integer? Hey, we had a look at that before, and the answer is yes. So the G-con is not a bad idea in this context. Just remember that for later maths, eh? If you actually connect points, you're saying a fair bit about what's going on in Mathland. Okay, let's go down and let's have a look now. I want you to do a little bit of practice here. Okay, so here's your practice. Provide 3 different representations of each of the following in addition to the one that's given. So I'm going to help you here. So this is a structure table. Let's just write them out. This is a structure table. Then we can have an algebraic expression. I want you to see if you can work one out for that. Algebraic expression. Then we can find a table. And you can make this up by hand or on the calculator. It's easier on the calculator. And then we can make a graph, a graphical representation. Okay. And you might try one of those by hand as well, see how good you are on a grid. Or you can do it on the calculator. You must be able to do both. So there are the 4 representations. Okay. So I want you to pause the presentation and try to do the other 3. Okay, for this one, this is a structure table. So I want you to try and get the other 3. And I'm not going to tell you the answers to this. This is something that you've got to do and put in your book so your teacher can have a look at it. Okay, and compare it to your mates there. Okay, so there's part A. Pause it, have a go. Now I'm going down to part B. Okay, there's B, a similar one. C and D are starting at a different point, are starting an algebraic expression, and you are to produce a structure table, an ordinary table, and a graph. Whatever representation is missing, you've got to do all 3 of those. Okay, pause it and have a go at each of those, compare. And then in part E, this is a bit of a challenge, mate. I'm going to give you a table. There's the generation number, value of x. Here is y. But what does y equal? Look at this. They've left out the algebraic expression. This is going to be hard because what you're going to have to say is what do you do to x to make neg 3? But it's got to be the same the whole way down, doesn't it? You've got to do the same to 2 to produce 0. Wow. Okay. I don't know. If you want to be a bit tricky, you could try and suss it out, or you could maybe draw a graph first. Well, you could do that in stat mode. You can't do it in table mode, can you? Because you don't know the formula to put in there. But you could also do it by hand and see if you can see a pattern on a graph. All right, I'm going to leave that up to you. Fair challenge there. What do you do then to 3 to get 3? 4 to get 6. But they've all got to be the same family, aren't they? So you're going to have to put down the same algebraic expression up here, make up the algebraic equation, if you like, equating the family member to that one. Okay, there you are. Pause it and have a go. Well, I'm going to go on now and have a look at another little thing I want you to see now. Coming up here. Here we go. Something for you to practice. Part 4. Provide 3 different representations. So here we are. We've got, this time, you say, oh, I'm thankful for that we've got the algebraic expression. That makes it easy. Okay, see how y is creeping into our family name now. Our family member is y. Okay, so we've got those 3, and you're to make a structure table, an ordinary table, and a graph. Okay, and you can use a calculator if you want to. And what about this one here? Provide 3 different representations. So you've got to find a table. That might be the way to start. listing down the x values and the y values in a table. Okay, you can't do it on the calculator because you don't know the equation for this family. So you maybe list it down by hand. You've got the graph, then the hard ones to work out the what? The equation, or the algebraic expression, and put it equal to y, making an equation, and the structure table. Okay, you've got to work those out from our table here and our graph. Wow, that's a fair challenge. Might need a little bit of help, but I did tell you, didn't I? As you go across and up, that's got something to do with it. If that's a straight line plot there, then you know something about those. I'm going to leave you to suss that out. You might have to get some help from discussion with your friends and also your teacher on that one. All right, we're nearly finishing. Hey, I hope you're getting excited at how far you're going with this stuff. It's really good to see you getting on in there. Okay, let's go down. And here's some interesting challenges for you. I want to go back because this was an introduction to a family's approach to algebra. Do you remember the P28 family? That was a family of rectangles, remember that? And people drew all sorts of different rectangles. Okay, some skinny ones and so on. They all had a perimeter of 28 centimetres. So they were the P28 family. Okay, perimeter 28 centimetres. Okay, we've got this rectangle here. Now that's what you build up, and you don't need to do another one. You can try to remember. But what we're going to do is to go down to this hint, because we want to try and make a algebraic expression that represents the area of all the possible rectangles. Hey, could we make an equation? What about calling the area big A? Hey, we could make an equation for this, not just an expression. The area could be called, it's a varying quantity, so it could be A, and we want to see how it varies as our x varies. What's our x? Come down here. How did you work out the size of the rectangle you drew? Suppose you wanted to draw a rectangle of width 2, how long would it be? How did you work this out? Or if you wanted to make a rectangle of length x. Okay, so you do this in two ways. You could say, well, everybody's family member was generated by different x values. So here, you could call the length x, or down here, they're suggesting the width be x. Okay, so you can do it either way. And what we want to work out, if we've got 28 centimetres all around the outside, the perimeter, what do these become? If you put x there, what's that going to be? And then how do you work out this? And then you've got to remember, A is, hey, I reckon I'm going to go L by W. Hey, more pro-numerals? What's he doing here? Well, that's fair enough, because you've got to put in different values for the length and different values for the width to get the area. Okay, so there you are, area is length times width. I wonder if you can prove that, or do you just accept your previous teacher's formula there? Can you prove that the area is length times width? All right, well, that's an interesting one. I think we'll stop and actually have a go at showing that. So what I want you to do is to think about that, but I want you to watch me have a look at why is the area equal to length by width. I think that's interesting. So come right over here, over on this side, and let's just unpack that a bit. Okay, so if you have your rectangle here, your first job, that's not a very good rectangle, your first job is to say, what does area mean anyway? Okay, we're more like this. What's the area mean? Well, it's the amount of space contained in this two-dimensional figure. How do we measure it? It's usually how many square centimetres can fit in there. So a centimetre square, a centimetre by a centimetre, is called 1 square centimetre. So it's those little boxes there. So that sounds a good way of measuring the area, how much space the shape covers in 2D land. How many of those squares can you fit in there? So let's try it, okay? Let's try it. Oh, this is getting very hard. I've got to do all these. Wow, there must be an easier way of doing it than counting up the squares. Okay, now we're going to add up, so we could add up all the squares in there. And I think there's a better way of doing that. Let's have a look. If we put them all in, let's say this is L, length, and this is W. All right, so we're going to put in, we're going to carve this up in W land, so there's W slices along there, and here in L we put it like this. Okay, so every row here has got, each row has L squares. Okay, because L is the length in centimetres. Okay, L centimetres. Now down here, how many rows? What we have W rows. Each one is a centimetre because W centimetres. So what have we got? We have W lots of L. Okay, W lots of L. Hey, hang on. I know in Mathland, lots of can be replaced by multiplication. So if we have 3 lots of 2, we say that's 3 times 2, we've got 6. So we've got, what's the total number of squares? The number of squares equals W lots of L. Okay, or L times W, if you want to think about it the other way around. Hey, that's not bad. That reflects again on the idea that when you use multiplication, you watch this word, multiplication. Okay, let's look at it. It's multiple, and this comes from addition. When you want to do many, many addings up, like all the squares in there, multiplication, multiple additions will help you out. Okay, so that's a quick way of doing many, many additions. Okay, well, I think we've just done something else there as well. We've said, well, come over here, see this formula that you were going to work with, and you still are in a minute. We need to go up the hierarchy and say, well, there's a way of doing it. Right? Just remember Huddy's hierarchy now over here. That's the rule or the algorithm for doing it. What's the concept? What's the idea? Do you understand that? And can you get up to the level of saying, I see it? Okay, so the rule was, stick the numbers in there, mate, and get an answer. And call it square centimetres. Or square metres, whatever the size is. What's the concept? The concept is what we've got over on the picture there. Over on this side, come over here. The concept is finding the number of squares in there. But if you want to see it, you've got to come down and see how the best way of counting up all the squares in there, which is the concept. The area is the number of squares contained within that shape. But now we have, I see it because I can see why you times. It's a quick way of adding up those squares. Do you get it? Now it's very important in your learning that you try to go up the hierarchy there. Don't just take rules and blindly use them. Now ask your teachers about, why does that work? How's that work? I want to see it. Okay, so here we are, coming back after all those ramblings on. What's your job? Okay, your job here is this. Write down an algebraic equation or expression. An equation, I want you to go for this over here, A equals, and instead of length and width, I want you to put down a connection with the width here, x, and what are the other sides in x land? What is that in terms of x? Okay, so that somebody coming along to you and saying, well, what's the area of my rectangle? Because I chose a width of 5 centimetres, you could actually put it into your mathematical equation and work out what that person's area was. Hey, that would be a good one. So I want you to try and do that now. You might need some little bit of help from your teacher or from classmates. I want you to put down your work so it's clear as to what's going on there. Okay, powerful stuff, algebra, isn't it? Starting to get exciting. All right, that's your first activity. I want to take you down below here and after you pause that and had a go, and have a look at another one. Okay, so here we go. All right, here's your first activity, part of this activity, and we're going to make 4 folds by following the following rules on a piece of paper or cardboard which is 10 centimetres by 10 centimetres. Got to be a square there. Okay, 10 centimetres by 10 centimetres. So this overall distance there is 10 and this is 10. All right, now, so you've got to do the first fold, T to U, so you fold along this line here. There is a rule though, TP must equal PU. Now, you don't have to do it like the one opposite. It could be small or large in length. Be an individual. If you do what you want, fold it a length you like. Okay, then you fold U to V. Okay, get rid of this. U to V, and that's this one here along this edge. You're going to fold that. And the same thing is that this equals this, and so on around the figure. Okay, so it's just making a mark there and folding along the line, so you get this coloured shape in the middle. Well, it can be different shapes, won't it? Depends on how big you make this. That will, I'm about to say it, that will generate different shapes. Well, that might be useful for what I'm going to do later on. Okay, so as you do that, they are members all of one family, aren't they? Okay, because you did the same sort of thing there and there, there and there. I wonder how you would think of generation numbers here though. What would the overall shape you get depend on? How was it generated? Okay, how was it generated? You all would start with this. I want you to do more than one. I want you to do about 4 of these, all with different generation numbers. What was the thing that drove the whole aspect? That was X, and that had to be X, wasn't it? And then I think you've set it all up after that because you've made these marks here. Okay, and just make sure that you see that once you've done that, this is set and this has to be equal to that top row there. Q must be equal to QV. Okay, so you start the ball rolling up the top here. All right, what I want you to do is to calculate the area. You can compare with your classmates, or if you're doing it at home by yourself, do 3 or 4 of these and see how the area varies as you change this amount you come in up the top there, the X value, the generation number, if you like, of generating these different shapes. They'll be in the family of, what, 10 centimetres squared paper shapes or something like that as your family, as your surname, sorry. Calculate the area of the quadrilateral. So that's going to be quite hard. The area of this irregular shape in the middle here, I'll just get rid of that. And I want you to actually calculate it with numbers when you have measured, so I'll use nice numbers here, measured how many centimetres there are there. And now your job is to calculate that area in the middle. Can you please see that it's not just a rectangle, so it's not length by width? I don't know, you might need to use in some way the area of a triangle, which is a half base times height, if you can work that in. And again, talking about Huddy's hierarchy, can you actually prove that the area is a half base times height? Okay, I'm going to leave you with that. I want you to do 3 or 4, compare it to other people if you can. And what do you notice? There's something interesting you should notice there. All right, pause it, have a go at that, discuss it, and I've got something I want you to do with it now. Okay, coming down here. So you've got quite a few of these little creatures. And what did you notice? Okay, what did you find out down here? What do you think you found out about the area of PQRS? Oh, did you find anything? I think you found the area was equal to, it seemed to be rotating around 50 square centimetres, wasn't it? Hey, is that possible? You did all these different ones, but still the area in the middle here, the area in there, came to 50? Is that what you found? Hey, how can that be? Could we prove it using algebra, perhaps? Okay, so here we are. I want you to call this x and x as before. I want you to write down an algebraic expression for the area of triangle PAQ. So that's this one up here. Okay, and also for QBR. Okay, and QBR, I'll have to come, hang on, we'll just go up a bit, just a little bit there. QBR is this one, and then PQRS. Can you do that? Okay, so I want you to try to write down in algebra land algebraic expressions using x. Okay, so you're going to have to work out what these are with x's, and finally get an algebraic expression for PQRS in the middle there. Can you do that? Okay, think about these hints and where does it go, and then see what that algebraic expression looks like, and how could it ever come to 50 for all x's? Pretty challenging stuff. So you might certainly have to talk to your teacher and classmates about this one and share the ideas and see where it's all going. I think algebra is going to be a real good tool to do problem solving and stuff like that. Okay, so I hope you're enjoying yourself. Hope you're not getting too much of a headache. Keep up with the challenges there and get rid of this one. And I'll catch you in a later presentation as we go further into the area of maths called algebra. It's good fun. See you then.